We humans are single processor creatures. We only have one brain. That means we cannot really do multiple tasks simultaneously. But we can switch between the tasks so quickly that gives an impression of multitasking. Multithreading in Java, which is quite a vast topic, is kind of along the similar lines. If there is one important topic in the entire Java ecosystem, it has to be multithreading. In this chapter, we'll learn everything you need to know about Java multithreading. We'll go over thread lifecycle, join and sleep, Daemon threads, thread priorities, shutdown hook, synchronization, which is a critical topic. We're going to talk about static blocks and static synchronization, volatile and happens before relationship, inter-thread communication. We're going to talk about deadlock and a lot more coming right next.
In this chapter, we're going to talk about multithreading. Before we understand what is multithreading, let us try to understand what is multitasking. Take a look at this example. Let's say there is a person and he is watching TV. While he's watching TV, he's also able to eat popcorn. And when he's doing both, he's also able to attend a call. As per this person, he thinks that he's performing all these tasks simultaneously. But actually, his brain is allocating few seconds of time on each one of these tasks and is switching between the tasks so quickly that the person feels that he is doing all these tasks simultaneously. For example, his brain is allocating 2 seconds of time in watching TV, say 3 seconds of time eating popcorn, and a few seconds of time in attending the call. And it switches between all these tasks so quickly that the person thinks that he is performing all these tasks simultaneously. Same is the case with computers. If you have a computer with single processor, and the reason why you're able to run so many applications at the same time, like Photoshop, Microsoft Word, or any game, is because this processor is allocating some nanoseconds of time on each one of these applications, or let's call it processes, and it switches between all these different applications or processes so fast that as a user you feel that you're able to run all these applications simultaneously. So in both these cases there is no actual simultaneous behavior. So when does computer perform tasks simultaneously? Is when you have more than 2 processors. Although you have one single physical processor, it can have more than 2 cores. A core is just a logical division of a processor, and each core would act just as another processor. When you have a processor, a physical processor with 2 cores, that means your system can perform 2 processes or 2 applications simultaneously. So now you can run Photoshop and Microsoft Word simultaneously, where each processor is dedicated to run one application or a process. It's as good as having 2 brains, and each brain is allocated to one task. Now since we're able to perform 2 processes simultaneously, this is called process-based multitasking. Another type of multitasking is called thread-based multitasking. Let's see what it is. Let us try to understand what is a thread. You can think of thread as a sub-process. For example, let us consider Microsoft Word. In Microsoft Word, there's a process that takes in the input from the keyboard, from the user, and that's why you're able to see the text. And there could be another process running behind that will check the spelling of whatever you type. So each one of these sub-processes can be termed as a thread. Whereas from programming perspective, it's an individual piece of execution of a program. Let me just explain you what I mean. Let's say you have a Java program, and say you have instructions on downloading a file, and you have instructions that will do some math. Now both these sections of code are completely independent of each other. We don't want this section of code to wait for the file to get downloaded, because this section of code has nothing to do with file download. So what we can do is we can separate both these sections and run them as two different processes or sub-processes. In our example, if you were to write the source code for Microsoft Word, then you'd have two sections of code that will do both these tasks simultaneously. So you can think of thread as a sub-process when you run the program, whereas from programming perspective, it's an individual piece of execution of a program. So what is the actual purpose of multi-threading? Let's say you have a processor with two cores, and let's assume that you didn't program with multi-threading in mind. Now, if you run this program, this entire program will be run only on a single logical processor, while we keep the second processor idle. But whereas, if you code with multi-threading in mind, you would identify sections of code that are independent of each other and you would run them separately. Your program will utilize both these processors, and each thread would run on each one of these logical processors. So that way, if it takes 10 seconds to run the program, with multi-threading, you would run it in only maybe 6 seconds. So the basic purpose of multi-threading is to make the most out of existing processors, and that's how we improve the performance. We're going to take a look at an example where I demonstrate you the utilization of the processor with multi-threading and without multi-threading. Now, since we're able to run multiple threads simultaneously with each thread on each one of this processor, this is called thread-based multitasking or multi-threading. Hope that makes sense. See you in my next video. In this video, we're going to take a look at how we can create a thread on our own. For this purpose, please import the project Multithreading into your workspace and open up this file, main thread example. All I'm doing here is I'm just throwing a simple exception, which is null pointer exception, and the reason why I'm doing so is because to demonstrate you that so far, although we haven't explicitly created threads on our own, JVM has done that for us. By default, JVM will create a thread called main. And that's the reason whenever you have an exception, you would see a message that starts with an exception in thread main. Let me just show you what I mean. Exception in thread main. That's because JVM has created a thread which is main thread. Now let's see how we can create threads on our own, a separate piece of execution of a program. In this example, I'm doing something in here, and I'm also taking the time when the program starts and the time when the program ends, and ultimately I'm calculating the difference between both the time just to see how much time it takes to run this program. In here, I have a couple of for loops which are very similar, and what I'm doing here is I'm trying to do some math that would ultimately utilize the CPU. So doing this math is quite CPU demanding operation, and that's exactly what I wanted. Let me run this program, and it's going to take quite a lot of time. Maybe I'll just pause the video and come back again. So it took a total of 76,000 milliseconds, which is, when converted, it's 76 seconds. Now let's see if we can improve the execution time by using multi-threading. Now just by looking at this code, I could identify two sections of code which are completely independent of each other, and I think we can run simultaneously. Can you identify those two sections? It's simple. These two sections are exactly identical, so that means we can perform these two sections simultaneously or concurrently. Let's see how we can achieve that. There are two ways to achieve that. One, by implementing a runnable interface. This is just a plain class file, and all I'm going to do here is I'm going to implements runnable. Now by doing so, I'll be forced to add all the unimplemented methods. The runnable interface has only one method defined, which is with the name run. This is the method where all the magic happens. All you want to do here is you want to insert the code that you want to be part of as a separate process, or whatever I'm saying as the individual piece of execution of program, you want it to be here. In this case, it's going to be this. Let's do Control C and Control V. Pretty well and good. Let's also track the time. I'm going to take the start time and the end time, and ultimately I'll find the difference between the two. But before the start time and end time, I need to do something. Somehow I need to create a new thread and run this set of instructions twice. And for that, I have to create two threads that run simultaneously, and both the threads will ultimately run the same piece of code. The reason why I'm running the same piece of code is because that's exactly what we're doing here. We have same piece of code running twice. In this case, this code will have to wait until this finishes. But in this example, I'm going to do them concurrently or simultaneously, and that can improve the overall time of execution. Let's see if that's the case. So I'm going to create an object of a thread class. I'm going to call it T1 equals new thread. Pretty well and good. I need to create another thread. Let's call it T2. Save the file. In order to start the execution, we're going to say T1.start and T2.start. In our next video, we'll understand what this start method exactly does. But for now, you can think of this as this will actually initiate the execution of the thread, basically execution of whatever the code that you have inside this run method. But here we are lacking something. This thread is not aware of this code in the run method. The way we convey that is we need to create an object of the class where the run method is implemented. New runnable example, and we're going to pass this object to the constructor of the thread class. That's all there is to it. Now what we have exactly done here is we sort of created a couple of threads and we have initiated them, and these two threads will now run simultaneously. But we have a problem with the timer here, because as I said, the main itself is treated as another thread. So although we have explicitly created two threads in here, we've actually have three threads in here because one is the main thread. So if you run this program, while these two threads are going on, our main thread finishes and it prints the time. We don't want that. What we want to make sure is that only when these two threads are not actively running do we want to go ahead with the rest of the instructions. So for that, we're going to use the method called isAlive. I'm going to use a while loop t1.isAlive or t2.isAlive. So in our main thread, we always continuously check to see if either of these two threads are alive. If they're alive, then just keep looping. And once these two threads come to a dead state, which we'll talk about in our next video, that means we're done with execution of these threads, then the isAlive state will return false. When both of these are false, then we'll exit out of this loop and would ultimately calculate the end time and would print the total time. Now let's see if there is any improvement in the time. Let's run the program. Again, I'm going to pause the video and we'll get back. Here it is. While it took 75 seconds or so without multithreading, with multithreading it just took over 38 seconds. It's almost half the time, and that's exactly the beauty of using multithreading. Let us take a look at one another approach where you can create multiple threads. You can create threads either by using runnable interface or directly extending the class thread, which I have done here. In fact, you're going to have exact same code in here. Let's do Control C and Control V. Going to have exact same code in here, and instead of implements runnable, you're going to say extends thread class. Let's change the name of the class name to thread class example. Now this time you don't have to pass in the object. In fact, you don't even have to create a new thread object. Let's delete it. Instead, you can use object of the same class to call the start method. The reason is we have already inherited all the properties and behavior of the thread class. Of course, this name needs to be changed to thread class example. And if you want to create another thread, then you can just create another object. Let's call this object 1 and object 2. I'm going to start the thread of object 1 and I'm going to start the thread of object 2. Same thing goes in here. Let's run the program and you would pretty much get the same output what we have got in our runnable example. Let me pause the video. There it is. It just took 38 seconds. So which approach should you follow? Should you implement the runnable interface or extend the thread class? I would recommend you to always go ahead with implementing runnable interface. One good reason for that is if you use an interface, you still have the possibility of extending another class. In this case, since you have already extended a class, which is the thread class, you cannot extend any other class because Java does not support multiple inheritance. Also, in terms of good design practices, it's always recommended that you use runnable interface. We'll see why in our examples pretty soon. Now, talking about the CPU utilization, I said when we use multithreading, we would improve the utilization of the CPU. Let's see if we are right. And for this purpose, I have opened the task manager for Windows. I'm not sure what it is for Mac users. So this is the current graph of the CPU utilization. Let me run the program without using the multithreading and see how the CPU spike looks. The utilization is around 39%, 38%, and it's going to remain same for 75 seconds or so. Let me pause the video. So this is how it looks. The CPU utilization is fluctuating between 31 to 39 and is kind of stable in that range. Now let's see the CPU utilization when we use the multithreading. Let's run this program and go to Task Manager. Take a look at that. The utilization has increased to 67%, 68%. It's fluctuating somewhere around there. Let me just pause the video and get back. That's it. we're done. So we got maximum utilization of CPU when we've used multi-threading. That's because each one of these threads would run on individual processor cores. Alright, let's continue in our next video. Alright, let's continue. Now this is not the best example I could demonstrate. In this example I have exact similar code in two places, but most often this could be two different operations but are still independent. Let's say I want to get rid of one of the 0 in here. Ultimately, the point I want to make here is these two are two different operations but are still independent. Maybe you would want to do download of a file here, and you're doing something completely independent, which is, say, you're reading some text from a stream or whatever. For this example, I just excluded another 0 just to make sure these two are two different operations, or maybe I just play around with these numbers, maybe say 4, 4, 5, 5, whatever. Now let me just copy this file and create another file. Let's call this with the same name, appended with number 2, and for your reference I'm undoing all the changes. Let's close this file. Let me open this file. Now I have identified two sections that are independent. How do I multi-thread them? I'm going to use the same class, but this time I'm going to create two of them. In one, I'm going to copy this section of code and paste it in the run method. And in another, I'll have the other independent code just like so. And all I want to have here in these two classes is just the code that I want to multi-thread. I'm going to get rid of all this public static void main and stuff like that. In fact, I'm going to do Control X. Let's create a new class file. Let's call this some name, whatever the name that you want to give, and I'll paste in the code in here. I'm going to create one object of this class and another object of this class. Let's call this object 1, and object 2 is supposed to go in here. There it is. Let's try to run the program. Let me pause the video and get back. Here it is. From design perspective, if you use the thread class, I mean extends thread, then you're sort of encouraging the developers to extend the behavior of this class and play with it, which is definitely bad practice. But whereas if you implement runnable interface, then it would sort of signify the developers that they're not supposed to do anything other than what you want to multi-thread. Which means in this class we only want that independent piece of code that we want to execute as a separate thread. So always it's better that you use implements runnable than extends thread, and you can have as many classes as you want that implements runnable, and each one of those classes perform a separate independent task. Hope that makes sense. Now let's talk about call stack. We know what call stack is, and every time we get an exception, we get the call stack from the method where the exception originated to the main method. The reason is that call stack is specific to main thread. Similarly, when we create our own threads, a separate call stack would be created. So now whenever we have an exception in one of these threads, let me just explicitly throw an exception in here. Throw new null pointer exception. And if you run the program, okay, looks like we need to have it at the end. Let's run the program. This time, again, a lot of wait time. It says exception in thread 0. That's the name thread scheduler named the thread. We'll talk about thread scheduler in our next video. But that's it. That's all I wanted to talk about in this video. See you in my next video where we'll talk about thread lifecycle. In this video, we're going to take a look at the thread lifecycle. If you run the multi-threading example we've seen in our previous video, this is exactly what's going to happen. When the interpreter comes across with the line new thread, we're creating a new object. So that will essentially create a new thread. And when we call the start method, the thread will go into a state called runnable. What this means is a component called thread scheduler can now schedule a task to run this thread by calling the run method of that object. Talking about the thread scheduler, a thread scheduler is a component that is not completely part of either operating system or the Java virtual machine. It's a combination of both. Ultimately, the job of thread scheduler is to manage all the threads in the thread pool. So once the thread comes into runnable state, the thread scheduler can now ask the processor to process instructions inside the run method of that thread. Once it does so, the thread will come into a state called running. And there are three possible state changes when the thread is in running state. One is dead, meaning all the instructions inside the run method were successfully executed. And now the state of the thread is dead. That means it's no longer there. Or there could be possibility that a running thread can get into a state called blocked or waiting. A thread can change its state from running to blocked when it is waiting for a resource, for example, a file. And that's the reason why it is important that you close the file stream once you're done with it, because there could be n number of threads which might be needing the same resource. So until the resource gets freed, the thread will be in blocked state. A thread can also get into a waiting state when it is waiting for other priority threads to finish executing. We'll talk about thread priorities at a later point of time. And a thread which is in running state can go back to runnable state depending on time slices of the processor. And a thread which is either blocked or in waiting state can go back to runnable state once the resource for which it is waiting for is freed, or after all the priority threads came to the dead state. So that's how the life cycle of thread works. It's as simple as that. See you in my next video. In this video, we're going to talk about anonymous in our classes and see how we can improve our multi-threading code using them. Take a look at this example. I've just created an object of class dog, which is having a method called bark, and that just prints the message barking. And in here, we're just calling that method. If you run this program, you would obviously see this message. But let's say I wanted to override the method, override the behavior of this dog right here, only for this time. So as you can guess, for that I need to create a new class Let's call it dog extended, and I'm going to use the keyword extends dog, and I'm going to give a different behavior. Now if I run this program, you would still see the same message, but if we have the parent class reference type and make it point to the child class object, now the behavior is going to change because of the polymorphism. Now if you take a note, this is the only time I wanted the behavior to be overridden. And even though if it is just one time I wanted to override the behavior, I still have to create another class and override the method. This is quite a tedious job. Fortunately in Java, we can override the method then and there itself wherever we wanted to attain a different behavior. And we can do so by using anonymous classes. An anonymous class is just as a local class that is local to a method, except it does not have any name to it. So what that means is we can use this entire block without copying the name of the class and have it in here. Let's comment these two lines. This has created an anonymous class, but we have a problem. We also need to tell the compiler for which class are we overriding the behavior. So we need to tell the compiler the parent class of this. And the way we convey the compiler the same is by using this statement like so, and we need to end with a semicolon. Although this statement looks like we have created an object of the dog class, actually it's not the case. We have actually created an instance of the anonymous class that does not have any name, and that anonymous class is actually the child class of the dog class. And we're assigning that object to the reference type of the parent object, which is the dog class. If it sounds confusing, go back and listen to my statement again. But whereas if you get rid of these curly braces, this is a different story. This is like you have a reference type of dog and you're pointing to the dog object. But if you have curly braces and you have overridden method like this, then what this means is you have actually created an anonymous class that does not have any name, and you have overridden the method of the dog class, which in this case is bark. Now you can use this object to call the bark method, and we get the result of the overridden method. Let's run the program. There it is. So now we can easily get rid of this class dog extended altogether. So that's the beauty of anonymous classes. In fact, since this is the only time you're calling the bark method, you can actually get rid of the reference type in here and just call the method bark directly like so, and it will still print the same. Now why am I explaining this? Let's see how we can improve our multi-threading code. Now see, I have created a new class which is runnable int example 4.java, and I have the exact code as to that of what we had in our other runnable examples. And in our anonymous class example, I've created an object of this class, and I'm passing that object to constructor of thread, thereby we are creating a thread. Now this is the only place where I want the method of that interface runnable to be overridden. Why should I create a new class for that purpose? So what can I do? I can certainly make use of anonymous classes. I'll copy this code from here and let me get rid of this. paste it over here, this will create an anonymous class, but compiler will expect us to tell for which class we have overridden this method. In this case, it's runnable. Runnable, new, runnable. Let's end with a semicolon. And now we can pass this object to the thread, and everything works perfect. And we can now certainly get rid of this class in here. Let's run it. There you have it. Now let's try to make this code a lot cleaner. I'm going to move this entire functionality to a method. We'll call it public static sum method, and I'm going to paste the code in here. Of course, we need to have the written type, and I'll call that method from here. Now if you take a note, the constructor of the thread class is going to take the object of the class that implements runnable. So instead of passing the object, I'll straight away create the object right there. There is no problem or whatsoever. Let's get rid of this semicolon. Now there are two things that are very obvious to the compiler. Compiler is aware the kind of object that we are passing to this thread constructor. The compiler is also aware that the only method that we can possibly override is the run method. With Java 1.8, with the introduction of lambda expressions, we can now get rid of all these unnecessary details that the compiler is aware of. So we can get rid of this object declaration here and the ending curly brace. We can also get rid of this method definition, including the keyword override. Now this is pretty well and good. We can get rid of the semicolon from here. The only thing that the compiler wants us to specify is number of parameters that we are passing to the method sumMath. In this case, there are none. So we need to tell the compiler by using the Java 8 lambda expression, like so. We have dedicated an entire chapter talking about Java 1.8 features. Until that point, you don't have to invest too much time in understanding Java 1.8 features. Just try to understand what I'm doing here. Now there is one more improvement we can do. We can get rid of this reference type in here and directly call that method start. This will do everything. Isn't that wonderful? We have significantly reduced the lines of code, and we haven't created another class implementing the runnable interface. That's the beauty of lambda expressions. Now again, we'll talk about lambda expressions and all the Java 1.8 features at later chapter. Now in future, let's say you wanted to create another thread. All you have to do is Ctrl+C and Ctrl+V. Give this a different name, sumMath new, and we're going to provide the behavior. For the sake of example, I'm just copying the same code, but make sure you do some task in here, you do some other task in here, and both these two tasks should be independent of each other. So now by using anonymous classes and lambda expressions, we have significantly improved the readability and the maintainability of the code. Of course, at a first glance, the lambda expression might look confusing, but once you're used to it, you will learn the comfort of using it. Alright, one last thing that I wanted to tell you is this lambda expression is only applicable when you have an interface that has exactly one method. Talking about the runnable interface, it just has one method, which is with the name run. And that's why we're able to make use of the lambda expressions. And these kind of interfaces with just one method are called functional interfaces, which were introduced in Java 1.8 specifically for usage with the lambda expressions. Let me just show you a quick example of a functional interface. Let me create a new interface. And let's have one method defined, void some name. In order to make this interface a functional interface, you can use the annotation functional interface. And that way, if you try to create another method, if you try to define another method, that's going to show us an error saying invalid functional interface annotation. This example is not a functional interface. So the developer cannot add another method accidentally, because we might be using this interface in our lambda expressions throughout our project. Hope that makes sense. See you in my next video. In this video, I'm going to talk about the join method. The join method waits for the thread to die. Let me show you what I mean. Let's create a thread for this purpose, and I'm going to use anonymous class for that. So I say thread t1 new thread, and inside it I'm going to say new runnable. If you choose this runnable interface and hit enter, then Eclipse is going to do the job for us. It's going to give us the skeleton code of the anonymous class with the only method that needs to be implemented, which is run. And in here we can have our code. Sysout, I'm just going to say from t1, and from here I'm going to start the thread, and after that I want to print a statement that this message is from the main thread. Let's run the program. Looks like the main thread finished executing before the thread t1. Now let's say we wanted to pause the execution of the main thread until the thread t1 finishes or come to a dead state. You're going to use the join method of t1. And this method is going to throw interrupted exception. Let's use throws declaration. Ideally you're supposed to handle it. Now when the interpreter comes across with this line, the interpreter will pause the calling thread, which is the main thread, and it waits for this thread to get finished, and once it's done, once the thread t1 comes into dead state, only then will it go ahead and execute rest of the instructions in the calling thread, which is the main thread. Now ideally, as per this program, we should let the thread t1 finish its task. So we should see this message, and then we see this message. Let's run the program. Pretty well and good. You can also tell the maximum time that you want to wait. So if I say 10,000 milliseconds, which is equivalent to 10 seconds, if the thread t1 is going to take more than 10 seconds, then the main thread will not wait. Regardless of whether t1 finished or not, it will move ahead after 10 seconds. In this case, definitely we don't have instructions that will take more than 10 seconds. So let's run the program. Pretty well and good. Now let's do something in here that will keep this thread alive for more than 10 seconds. And for that purpose, I'm going to use the method called sleep, which is in the thread class. Thread.sleep, and you're going to provide the time that you want this thread to sleep. I would say 30 seconds, or let's make this 10 seconds, and let's make this 2 seconds. Again, this is going to throw interrupted exception. We need to handle it because this is a checked exception. Pretty well and good. So now in this case, we're waiting at max 2 seconds for the thread to get finished. But in here it is taking more than 2 seconds. Now ideally, we should see this message first, and then we should see this message from thread T1. Let's run the program. So the main thread waited for 2 seconds for T1 to get finished, and it went ahead with rest of the instructions. Meanwhile, after 10 seconds, even T1 got executed. Pretty well and good. Now let me demonstrate you something interesting. Let's get rid of this wait time. And I'm going to create a couple of more threads. I'll call these T2 and T3, from T2 and from T3. And here I'm going to start all those 3 threads. For now, let's get rid of this join statement. T2, T3. Let's run the program. Now all these threads, once we use the method start, they all go into runnable state, and it's up to the thread scheduler to decide which thread to prioritize. And it's at the moment not within our control. So what I mean by that is, every time I run this program, we would see different sequence of execution of these threads. This time it's main thread T2, T3 and T1. This time it's main and T3, T2 and T1. You see the difference, right? This time it's T1, T3 and T2. It's not predictable. However, sometimes you want to execute threads in sequence. Let's say I wanted to execute T1 first, and then T2, and then T3, and then the main thread. I can certainly make use of the join method. I'm going to say T1 dot join. So the main thread will pause right here before it goes ahead and starts the second thread. Same is the case here, and here it waits for T2 to get into dead state, and same with T3 in here. So now threads will go in sequence. Let's run the program. T1, T2, T3 and main. No matter how many times you run, the sequence wouldn't change. But what if I do something like this? Let's say I have all these join statements in one section and T1, T2, T3 in another section. Can you make a guess on the output of this program? Threads would execute in no particular order. Let me just show it to you. T1, T2, T3, T1, T3, T2. It's not certain that the sequence is always the same. The reason is, I said, when we say T1.join, the calling thread, in this case the main thread, is going to wait for T1 to get finished or come to a dead state. Since we use the join method, after we started all these threads started executing simultaneously. Hope that's clear. See you in my next video. In this video, I'm going to talk about Daemon thread. You can think of Daemon thread as a thread that runs in the background, and its major job is to support all non-Daemon threads. So what is a non-Daemon thread? Whatever the threads we have created so far manually are all non-Daemon threads. A good example of a Daemon thread would be garbage collector thread that is initiated by the Java virtual machine. The job of garbage collector is primarily to destroy the unused objects and free some memory for future objects. And there is no need of garbage collector once all the non-Daemon threads are executed including the main thread. So JVM, before it shuts down, it will forcefully kill all the daemon threads, no matter what they are doing at that point of time. You can create a daemon thread on your own, but keep in mind the things that I've just mentioned. And one real-time example where you would want a daemon thread is when, say, you're developing a backup software where it will copy all the files in your system to a remote server that you configure. In that case, you might want a daemon thread running behind the scenes that will constantly poll the remote server to check to see its health. I mean, if the remote server is disconnected or maybe ran out of space, then you would want to notify the user with a message on his screen. Another good example would be, say, you are developing a game where people from across the globe will play together as a team, like Counter-Strike. Then in that case, you might want a daemon thread that constantly shows the position of all the players in a map to each one of the player. So basically a daemon thread is like a supporting thread, and the life of daemon thread is dependent on the life of non-daemon threads. So they basically live at the mercy of non-daemon threads. Let me just prove that point with an example. So I'm going to create a couple of threads. I copied the same code from our previous examples. Let's call this T2. And in here, what I'm going to do is I'm going to have an infinite loop. For example, I'm going to say for, if I do this, this is going to loop me through forever. And I'm going to do sysout from Daemon. And I also want to wait for a second. Thread.sleep 1000 milliseconds, which is equivalent to 1 second. I'm going to have a try-catch block. Let's get rid of all this unnecessary junk for the time being. And in our second thread, I'm going to wait for 10 seconds. From T2. Let's save the file. So basically what I'm trying to do here is I'm trying to simulate a behavior where we're constantly polling the remote server and doing something with it. Say we're checking the health of it. And for that we want the polling to happen forever and assume that we're doing something meaningful in here. Maybe if this was a backup software, then you might want to do copying the files or whatsoever. If you observe, the purpose of thread T1 is to serve T2. There is no real meaning of this running when the thread T2 finishes executing. So we want the thread T1 to be a daemon thread. Before we take a look at how we can make this thread a daemon thread, let's try to run these two threads simultaneously and see what's going to happen. T1.start, T2.start. Let's save the file. So in this case, regardless of T2 finished executing or not, this thread keeps polling. Let's run this program. So now both the threads got started and thread 2 is waiting for 10 seconds and is done. But still our thread T1 is going and it goes forever. We don't want that. We want to stop it the moment thread 2 is finished executing. So how do we make this thread a daemon thread? It's very easy. You just have to use one method in the thread class, which is T1, which is T1.setDaemon, and you say it as true. By default it is false. The reason is thread T1 inherited all the properties from its parent. Since the parent thread, which is the thread class, is a non-daemon object by default, the child will inherit the same. If you want this thread to be a Daemon thread, then you need to set it this manner. Now let's expect this thread to exit when the thread T2 finishes executing. Let's run the program. 3, 4, 5, 6, 7, 8, 9, 10. There it is. We're done. JVM has killed this thread T1. Also make sure that you set this thread as Daemon before you start the thread. If you do the other way, then it's going to throw an exception. Illegal state exception. Let's get rid of this. Stop the program. Also, it's important to note that you don't want to perform any crucial operations in the Daemon thread, because if you have a finally block in the Daemon thread, it will not get executed. So don't deal with streams in a Daemon thread unless you make sure that its finally block will be executed before all the non-Daemon thread finish executing. So that's it on Daemon threads. See you in my next video. In this video, we're going to talk about thread priorities. A thread priority defines which thread will take priority over the other. The threads with higher priority will have the higher chances of executing first. We can have the priorities set between the range 1 to 10, with 1 being the low priority and 10 being the highest priority. And the default priority for any thread is 5. Now let's see how we can set the priorities of all these 3 threads. I have the same example as previous, just that I don't have those join statements. You can make use of the method setPriority to set the priority for a particular thread. And I'm going to do the same. So before you start the thread, we can set the priority. Set priority, and you can give a numerical within the range 1 to 10. If you give any value that is not within that range, then you would get an exception, and we don't want that. You could either give a number like 10, 1, or 5, or you can make use of the constants that are defined inside the thread class. The max priority will have the value 10, the min priority will have the value 0, and the norm priority will have the value 5. So let's make use of these. I would like to give thread T1 the min priority, and for thread T2 I'd like to give max priority, and for thread T3 I'll give the norm priority. If I run this program, you may think that the thread T2 will get executed first because it's with the max priority, and then T3 and then T1. But that's not going to be the case. We may see different sequence every time we run, and I'll tell you why. Let's run the program. It keeps changing every time. The reason is, if you have say 4 cores in your CPU, and if you're scheduling less than 4 threads, then each one of these threads can run in one go simultaneously. Prioritizing a thread does not mean that the other threads will stop until the prioritized thread finish executing. If you want thread to wait until the child thread executes, then you can use the join method, which we have seen in our previous example. So it's just that we're telling the underlying operating system which thread in my application should take the priority, and it's with the mercy of the operating system the threads will be executed. And usually CPU tends to allocate more time in running the threads with higher priority. So setting the priority does not guarantee the order in which the threads get executed. And that's why you're seeing all these random results. If you want to see the real example of thread priorities, then have a CPU demanding operation on each one of these threads like we did earlier, and have say 10 threads running with each thread set to some priority. I bet you would see the priorities taking effect, and threads with higher priority will finish first. Alright, that's it on thread priorities. See you in my next video. In this video, I'm going to talk about shutdown hook. There could be instances where you might want to execute set of instructions when the program exits abruptly. For example, you pressed Ctrl+C when you're running the program from the command prompt, or when the interpreter comes across with system.exit statement. In these two cases, the program will stop abruptly and JVM shuts down. In both these cases, the finalized block will not get executed. But we can make use of the shutdown hook to execute set of instructions before the JVM shuts down. Let's see how we can do that. I'm going to make use of the same code from our Java IO chapter, which will read the file and write the data into another file using streams. And I paste it in here. It's exact same code. Now let's say for some reason I want to exit out of this program right here. I'm going to use system.exit with the status 0. The parameter 0 means that we are exiting out of this program without any major issues. Anyway, the point that I want to make here is if I run this program, by the way, let's have some statement written in here. Let's have sysout and finally block. This is just to make sure that the finally block will not get invoked in case of system.exit. Let's also have one sysout statement in here right before the exit statement. Let's run the program. There it is. Now let's use a shutdown hook. So right here or somewhere in here, I'm going to have this statement runtime dot get runtime dot add shutdown hook, and the parameter that it takes is the thread object. So we can copy the code from here. Let's copy this entire new object of thread and paste it over here, and that should do the trick. Essentially with this we are telling the Java virtual machine that before it shuts down, that means when system.exit happens or when the user presses Ctrl+C from the command line, then we're asking JVM to start this thread, whatever we have in here, and run it. Let's say from shutdown hook, save the file and now run it. Fair enough. The shutdown hook will also get executed when the program runs smoothly. For example, I get rid of this statement system.exit, and if I run this program, still you would see the shutdown hook getting executed along with the finally block. You can have as many shutdown hooks as you want, but the sequence in which these shutdown hooks will get executed is not within our control. If you want, you can also remove the shutdown hook. For example, let's copy this and make this part of a thread object and assign this to a thread reference type, and I'm going to pass this argument and say remove shutdown hook, and this will do the trick. Obviously you don't want to remove shutdown hook without adding it, and obviously you don't want to do them immediately. There has to be some valid reason why you want to remove shutdown hook. Maybe you can put this statement right after you're done with copying the file, maybe somewhere in here, so that the code inside the shutdown hook will not get executed after successfully running the program. Let's try to run the program, and there it is. We don't have this code executed. We have removed it. Alright, hope that makes sense. See you in my next video. In next couple of videos we're going to talk about thread synchronization. Multithreading has advantages on performance, but it comes with a price. If you remember, when we talked about JVM architecture, I've mentioned about various memory sections we have. We have heap memory, method area, method stack, PC registers, and native method stack. If you are not aware of any of these, I would recommend you to go back and take a look at my JVM architecture video. Of all these memory sections, heap area and method area, I said, were shared across all the threads, which also means if I instantiate a class, or in other words, create an object, all the variables in that object are accessible and are visible to all the threads that I create. This will create a problem called thread interference. So let me give you an example of thread interference. Let's say you have a class with one variable and is assigned with the value 10. Let's also assume that we have a couple of methods. In one method we're incrementing the value of I, and in another method we're decrementing the value of I. Let's also assume that we have another program which will have our main method, and in that I have a couple of threads created. Let's assume they are T1 and T2, and all I'm doing in T1 is I'm calling this method increment by creating an instance of this class example. Let's call that object obj, and using this object I'm going to call the method increment, and from thread 2 using the same object I'm going to call decrement. Now I do t1.start, t2.start. What is the expected output here? What I would expect is I will increment the value of 10 by 1, which will make it to 11, and then I decrement it back to 10. So the result I'm expecting is 10. But that may not be the case. Let me explain you why. In our memory section we have this variable set, which will be 10 as the initial value. Let's also assume that we are having a dual core processor, and on each one of this core, each one of these threads will run. So T1 goes in core 1 and T2 runs in core 2. In here I'm performing increment operation, and in thread 2 the decrement operation. Internal increment operation happens in 3 steps. Step number 1, it needs to read the value of I from memory, so it's read. And second, increment the value, and third, write the value back to the memory. And same is the case with decrement. We have 3 steps, which is read, decrement, and write the value to the memory. Now in our case both these threads are going simultaneously. Let's assume that thread 1 read the value from memory, so it read the value 10, and simultaneously even thread 2 reads the value from memory, which will be 10. Thread 1 increments the value to 11, and thread 2 decrements the value to 9, because that's what is read in here. Let's assume thread 1 finishes first and writes the value back to the memory. So it writes the value 11 in the memory. And when thread 2 finishes, it's going to write the value 9. It's going to overwrite this value of 11 and make it to 9. This is wrong. In case thread 2 finishes first, then the value would be 11. But it's not going to be the result that we're expecting, 10. This is a serious problem. We want consistency. This is called thread interference. With the modern processors, we may not be able to see this issue with our program, but let me just give you a couple of examples of thread interference in our current programming world. Let's assume we have a program, and in that I have a couple of threads, T1 and T2. All I'm doing from thread T1 is I'm creating a file and I'm populating some data in it. Let's say it's a text. Now from thread T2, what I'm going to do is I'm going to read the same file, the data inside that file, and do something with it. Let's assume that these two threads are running simultaneously. Now let's assume that I run this program. Now before thread T1 completes writing all the lines that it needs to write, thread 2 tries to access the same file, and it may not be able to get all the data because thread 1 hasn't yet finished. So let's assume that thread T1 is going to write 100 lines of code, 100 lines of text. Thread 2 may get only 10 lines of text or 20 lines of text. It could be any number, which is inconsistent. We want consistent way of doing things. And that clearly explains why multithreading is a problem. Another real-time example would be, say I'm writing code for flight reservation system. Now assume, using my software, you're about to book a ticket. And let's also assume that there is a flight with only one seat available for grabbing. You will place an order, the request comes in, enters inside my code, and this code will actually perform the action of reserving the seat for you. But like you, there are 100 other users who are trying to book the same seat. Now how do I handle this? If everyone places the request and if all the request comes inside this set of code, it might result in inconsistent behavior. Some of these users will get errors on the screen, or some of these users may get a message saying that their reservation is confirmed. While there is only one seat, it's not possible to book tickets for multiple users. So the first request that comes in is the one I need to process. I need to keep all the other requests in queue. And if for some reason, if the first request fails, the seat is still available, then I want to go ahead, take the second request and reserve the seat, whatever. Ultimately, we want consistent way of doing things. So what is the solution here? Before I talk about the solution, let me show you one interesting example. Let's say there is a changing room on a seashore. People love surfing in the water with sunset, and they wanted to come back and change their clothes. Let's say there are 10 people in the queue to change their clothes. If there is no lock in this changing room, then there is a possibility that 2 or 3 people can enter inside this room and thereby causing a clash. They fight each other. But let's assume that there is a guy who is hired to control the behavior of these customers, and his job is to allow only one person to enter inside that room. Now what is this guy going to do is he's going to carry one key, and he would give this key to only one person at a time, and they all stand in queue. The first person who is about to enter is going to carry the key from this guy, and he's going to unlock the door, enter inside, do something in here, and when he comes out, he's going to lock the door again and is going to handle it back to this guy. Let's call this guy monitor, as he monitors all the activities happening in here. And again, the same thing repeats. the second person comes in, takes the key, unlock the door, do something, and while exiting he's going to lock the door and handle it back to this monitor. And this way we're controlling simultaneous access to this room. Do take a note that everyone roams freely across all the seashore, but only in the changing room do they want privacy. So only one person is allowed to enter inside that room at a time. Now let's go back. So in this example, let's assume that this section of code is like the private room, and all these threads are like people standing in the queue, and at a time we want only one thread to be able to access this section of code by acquiring the lock of that object, and while it leaves, it's going to release that lock for another thread to get inside and execute. But all these threads are allowed to run simultaneously rest of the code. It's only within this section we want to restrict only one thread at a time to enter inside by acquiring the lock and release the lock when it leaves from that section of code. Same is the case in here. Let's say we have a code and two methods, and in M1 I'm trying to write some data into this file, and in M2 I'm trying to read the data from this file. Now if I make this section of code accessible to only one thread at a time using the locking mechanism, that means when T1 acquires the lock of that object, then no other thread can actually enter inside into either of these methods. And only when T1 releases the lock will the thread T2 can enter inside any of these methods. So definitely, without any doubt, this will solve our problem. So when T1 is executing that code, T2 will remain in waiting state. And once T1 finishes executing that section of code, T2 will get out of this waiting state and it is allowed to enter inside this code. Hope that's pretty clear. In our next video, we'll see everything in action. Alright, let's continue. I've created another project with the name Multithreading tool, and I'm continuing writing my examples in that. You might want to import this project to follow along. I've created this file and it has the code from our previous examples. All I'm doing here is I've created a couple of threads and I want them to run simultaneously. We also have created an object of the sync example, which we're going to use pretty soon. Currently this class is empty, but I'm going to introduce a method that will cause the problem of thread interference. So what I want to do here is I want to take the string as an argument and print each one of those characters in that string with the delay of 1 second. So public void display string str, and I want to use for loop to loop through all those characters. I'm going to use sysout char at the index I. This will print all the characters one by one, separated with a new line character, but we want to have a delay. Thread dot sleep, and I want to delay it by 1 second or 1000 milliseconds. We need to have a try catch block. Okay, let's use print instead of print ln. And using this object, I'm going to call that method from thread T1. I'm passing the argument apple, and I'm going to have the exact same statement even in thread 2, but with a different argument, banana. Now, can you precisely guess on the output of this program? We may get apple banana or banana apple, but that's not the case. Nobody in this planet Earth can predict the output of this. Let's run the program and see the crazy output. In this program we got bapan al, we got ba pa, etc. You don't find this word in dictionary. Now let's run the program once again. You may not see the same result. So this time it's A, B, A, P, P, N, A, L, whatever. So every time you run, the result is going to be different. But the point that I want to make here is it's very inconsistent and we need to solve this problem. And this is caused due to simultaneous access of this section of code by more than one thread. Now let's see how we can make use of the locking mechanism. Every object is going to have a lock on its own, and at a time only one thread can acquire that lock to enter inside that lockable section. We want to make this section lockable. This is like the private room or the changing room in our example. So let's do so, and for that purpose I'm going to have to create the lock. And the way I do it is like so. I'm going to use the interface lock, new, I'm going to say reentrant lock, and I'll do Ctrl+Shift+O to import the class. So basically this lock is an interface, and the implementation of that lock interface is done in here. So we have created an instance of this class, but we have the interface as the reference type. Now what we want to do with this, the first thread that's going to enter inside this section, we want that thread to acquire that lock. So I'm going to do log.lock. This can be any name, and once we're done, once that thread executes all the instructions in that, we say log.unlock. So now with this code, the first thread that's going to enter inside this section is going to acquire that lock, do whatever is instructed in here, and it's going to release that lock for another thread to enter inside this. Let's assume that thread scheduler decided to give opportunity to T1 first. So T1 will enter inside this, acquire the lock, perform all this, and while thread T1 is executing these instructions, T2 will be in a state called waiting. It's waiting for thread T1 to release the lock. Meanwhile, thread T1 finishes all these instructions, and when it comes across with this instruction, it's going to release that lock, and so is available for thread 2 to grab that lock. It goes on the same way for all the simultaneous thread for this section of code. So at a time only one thread is executing that section of code, and this should solve our problem. So we should either see apple banana or banana apple, whichever thread gets executed first. So thread scheduler gave opportunity to thread T1 first, and now thread T2 got opportunity in here, and we're done executing. Basically this is a bad practice of code. We want this unlock statement to be residing inside the finally block, because there could be possibility of having an exception in these lines. So to get rid of all that kind of mess, having to deal with locking, unlocking, and creating an object of lock, etc., you can get rid of everything in here like so. Instead you're going to use the word synchronized. This will make this entire code inside this method a private section. And not to be confused, private as in the private room example that we talked about, I'm not talking about the access specifier private. Please don't get confused there. Now let's run the program and expect a consistent result. It's apple and then it will be banana. Pretty well and good. Alright, let's continue. We were talking about multiple threads accessing a system resource, a file for the example. In this example, I have created a couple of more methods, and in the method write_to_file, I'm passing string as an argument. And with the file writer stream, I'm going to write each one of these characters on each one of the line into this file temp.txt. And for every character I write to the file, I'm making sure I'm flushing the data, because that's what is going to put the data from the buffer to the file. And then I'm waiting for 1 second. So for each character, I'm going to wait for a second. In another method, I'm doing read from file. So in here, I'm reading the data from the same file, but before doing so, I'm waiting for a couple of seconds just to make sure that something is written in here. So to demonstrate the inconsistency, I'm just explicitly waiting for a second and in here for a couple of seconds. And from our main method, I'm going to comment out these two method calls. Instead, I'm going to write something into that file. So instead of display, I'm going to say write_to_file. And I'm passing in some string. The method is throwing an exception. We need to handle it with the try-catch block. And in here, I want to call object.read from file method. Again, we need to handle the exception. Now let's run these two threads simultaneously. What I'm expecting is when the thread 1 writes a couple of characters, the thread 2 wakes up from the sleep mode after sleeping for a couple of seconds, and then it tries to read whatever is there in the file. And this would happen only if the thread scheduler schedules to run the thread 1 first. If it decides to run thread 2, then we get nothing on the output because there's nothing in the file by then. Let's run the program. So thread 2 finished executing and it printed the first two characters because that's what is currently written to the file. Let's run the program again. So thread 2 finished executing, but still the program is running. That's because thread 1 had to write all those characters. But the point I want to make here is when the data is being written, we're trying to read the same data from the file. So this is very inconsistent. Although we're consistently seeing the result because we have an explicit wait time here, but in real time you might experience very inconsistent behavior. So how do we deal with this? The solution is the same. We're going to use a synchronized keyword for these methods: public synchronized void, synchronized void. Now in this case, you can think of this as having two private changing rooms, and if one thread enters into any one of these rooms, or from code perspective, when one thread enters into any one of these code sections, it will acquire the lock. Once the lock is acquired by that thread, no other thread can enter into any one of these synchronized blocks. So in our example, when we call this method write_to_files, T1 is going to enter inside this and it will acquire the lock. Meanwhile, thread 2 will be in waiting state because lock is not available for it to enter inside the read from file method. Once thread 1 finishes executing this, then it will release the lock, which allows the thread to get out of the waiting state, and then it comes into runnable state, and thereby it qualifies for entering inside this section. Let's see if that's the case. And this would happen only if the thread scheduler schedules T1 first. Let's run the program. So T1 started first, and it is writing all the data into the file, and then T2 started, waited for a couple of seconds, and it read everything in that file. Now result is something meaningful. We're seeing the entire word, whatever we are passing in here. Let me quickly show you another example. Let's open this file. I already have some code written. I'm having a count in here. In one method, I'm just incrementing the count to say several times. Meanwhile, from another thread, I'm going to call this method readCount to get the current value of the count. Let's see what the behavior would be. So we're going to create an object of this class, or instantiate sync example2. Let's call it object2 equals new sync example2. As simple as that. Let me comment this entire code out by pressing Ctrl+Shift/, and then let's do the same in here. I'm commenting this code just for your reference. You may want to uncomment it and play with it. So let's use this object to call the method increment count, and from thread 2 I'm going to read the count. Let's run the program. Now every time you run the program, you're going to see inconsistent behavior. So when thread 2 read the value of the count, the value is 1023. This time it's 28,388. The number is very unpredictable. Very unpredictable. So how do we deal with this? What's the solution? As you can guess, we use the word synchronized for each one of these methods. By the way, internally synchronized keyword is going to do the job of locking and unlocking, just as the example we have seen earlier. It's just the convenient way of dealing with locks. Now let's run the program. See, we see a proper result every time. Pretty well and good. I think this explains us what is the side effect of using multi-threading and how we can get rid of it. See you in my next video. In this video, we're going to talk about static synchronized. I said a lock is associated with each one of the object. In this example, both these threads are referring to the same object, so there is no problem of thread interference because there is only one key associated with this object. But thread interference is still possible if these two threads refer to two different objects, as now each one of these threads hold their own object key. Let me show you what I mean. For this purpose, I have again uncommented these lines of code for accessing a file. I'm going to create another object. Let's call this, say, object 3. From thread 1, I'm using the first object, and from thread 2, I'm reading the file using object 3. Now both these methods are synchronized. Let me prove that to you. Synchronized and synchronized. But now thread interference will happen. Let's run the program. There it is. Clearly, it's a problem. So what's the solution? Let me show you. So what I'm going to do is I'm going to make these methods static. Now, by making these methods static, I can access these methods using the class name. So I'm going to use the class name instead of the object, like so. Let's run the program. and after that I'll explain you what I've just done. There is no thread interference and the result is as expected. The reason is, just like an object is associated with a lock, even the class is associated with a lock. When we make the method static, that method is basically associated with not with an instance of that class, but with the class itself. So that means when thread T1 enters inside that static synchronized section, it's going to acquire the lock of that class, and no other thread can get a lock unless the thread T1 releases that lock for that class. So in here we're calling that method read from file using the class name, as obviously this is a static method, and by then the lock is not released, so which will keep this thread in waiting until the lock is released from thread T1. Once thread T1 releases the lock, thread 2 acquires the lock and goes ahead with execution, and that's why we're seeing pretty good results. Alright, see you in my next video. In this video we're going to talk about synchronized block. Take a look at this example. Let's say I'm conducting a marathon event and say I have 5 participants. I have decided a route from source to destination, and on my route there are 5 lines, 5 lanes for each one of these participants to run. But somewhere in the middle of the route there happened to be a bridge, and only one person can fit into this bridge. Now let's assume that the distance between the source and destination is 20 kilometers, and it takes an average of 1 hour for a person to reach from the source to destination. Since somewhere in the middle of the route only one person can fit in, I have decided to allow only one person to run at a time. So for 5 people it's going to take 5 hours of time to complete the entire race before we announce the results. So just because of a particular section where only one person can fit in, I'm not allowing all the players to go simultaneously. But what if I allow all the players to go simultaneously until this point, and after that only one player will go at a time, and again they continue going simultaneously from this point. And this way I'm pretty sure I'm going to save a lot of time. So without this bridge, if it takes 1 hour of time for all the players, an average time, with this bridge, and if they go simultaneously until this bridge, go one at a time in this bridge, and then again continue with their simultaneous running, then only within this time where they run on this bridge there will be slight delay. So it would be more or less, say, 1 hour 15 minutes versus 5 hours. There's a big time difference between this and this. Same with the programming. Let's say you have thousands of lines of code and you have 5 different threads. Just because a section of this code requires synchronization, we don't want to make the entire code synchronized. As you can see, there is a difference in performance. It's going to take 5 hours to execute this code if we allow only one thread at a time. Instead, what we can do is we can allow the threads to execute simultaneously in this section and this section, but only within this critical section we want to allow only one thread at a time. So let's see this in action. Let's go to our workspace. For this example, I have created a couple of files, read1.txt and read2.txt. In read1, I just have apple as the text, and in read2, I have banana as text. Now from our program, I've created a couple of threads. From thread 1, I'm just going to call a method inside this class, sync block example, which I'm going to talk about in a while, and I'm passing the path to that file as an argument. We'll see what we're doing in this method. And in thread 2, I'm passing the read2.txt as an argument. By the way, we can also give the name to these threads like so. You just have to pass another parameter. In this case it's thread 1 and here thread 2. This is just to see which thread is doing what when we get the output. And I'm trying to wait for these threads to finish in our main thread just to be able to calculate the total time. In here, what I'm doing is, in the method, I'm just reading the data inside whatever the file path. I send it as an argument. If you go inside the read from file, it's just going to have the file reader and read the data from the file, and ultimately this method is going to return the string, which is the text inside that file, and that string is assigned to the string object, and we're passing that string, ultimately the text inside that file, whatever the file you provide in here, and we're writing that text into another file. So in our write to file method, we're writing that information to the temp.txt, and that's all we're doing. And every time we write each and every character, we're flushing it and waiting for a second, and whatever is inside the temp.txt file, whichever we have written, is going to be read into this another string variable, and we're trying to print it, show it on the output along with the current thread details. And this is where we would see our thread name. Alright, that's all we're doing. Now we're not having any kind of synchronization functionality. Now let's see what's going to happen. The result is something really messy. Let's run the program again, and I bet you won't see the same result again. There you go. Let's run the program again. So result is very inconsistent, and it took around 6 seconds to execute that. That's because both these threads are running simultaneously. But as per our previous examples, let's synchronize this method. We want to put it before the void return statement, and I'll do control space to get the suggestions. I'll make use of the IDE functionality. But now let's run the program. Apple and banana. It solved our problem of thread interference, but at a cost of performance. It took 11 seconds versus 6 seconds. So basically, every time you use synchronized keyword, we are sacrificing performance that multithreading provides. So if you keep all the code under synchronized section, it's as good as having everything run under one single thread. As in our marathon example, we don't want to make every runner to run individually just because there is a bridge at some point of time in the route. It will take a lot of time to finish the event. Instead, only when the bridge occurs, we want the runner to go one at a time. Similarly, we can make our threads go one at a time in the critical sections of the code and let them run simultaneously in rest of the places. So as a rule of thumb, always use synchronization sparingly and only when required. So let's see what we can do to this code. If you take a look, you can easily identify that reading from file is not that critical. I mean, even multiple threads can execute these two lines simultaneously. Same is the case with sysout statement. We don't want threads to go one at a time for this piece of code. But whereas these two sections I feel are critical, and we don't want threads to write to the same file simultaneously. Now what we can do is we can get rid of the synchronized keyword in here and only make this section synchronized. How do we do that? You use the same keyword, and within the parenthesis you would provide the object. We'll talk about what you're going to provide in this parenthesis in a while, but ultimately we want to keep this code inside this section. Now when thread 1 and thread 2 starts executing simultaneously, they enter inside this method simultaneously, and they're going to execute these two lines of code. But when they come across with this synchronized block, whichever thread enters inside this block is going to acquire the lock of that object, while the second thread is going to wait until the first thread reaches end of the instruction inside this block and releases the lock. Once thread 1 releases the lock, it goes ahead with executing rest of the instructions, and meanwhile the lock is made available for thread 2 to enter, and it can gladly enter inside this section, and from that point on it will execute everything, rest of the code, along with other threads. Now let's run the program. Hopefully we'll see some consistency. I'm sure we do. Let's run the program. Thread 1, apple, that's what we had passed. That's what we have in that read1.txt, and thread 2, banana. Pretty well and good. Now you have seen a slight improvement in performance. We have got it done in 11 seconds versus 12 seconds. In this particular example, you may not be able to see big performance difference, but in high-end applications you would definitely see a big performance difference. You don't want the entire code to be synchronized, so you can only synchronize critical sections. Now let's talk about what we are passing in here inside this parenthesis. Let's say you have another section of code which is also a critical section that you want to allow only one thread to execute at a time, but it's an independent section. Let me show you what I mean. Let's say I wanted to call this display method from here, and for that we need to create an object of this class. Let's do that. Let's call this SE or whatever you want to call it, example. Now based on our previous example, we have seen that we cannot run this piece of code simultaneously, but let's say I wanted to call that method display, and I'm going to pass the exact same argument for the sake of this example. Now since this is also a critical piece of code, I'm going to do Ctrl X and Ctrl V here inside the synchronized block. But we have a problem here. This section and this section are completely independent. We don't want this section of code to be waiting until this section. So what we can do, we can make it part of another section, which as you can guess, a synchronized block. And instead of saying this, I'm going to pass this object, which is S, which is an object of this. Now if I run the program, only one thread is going to be allowed in both these sections, but these two sections can now be executed simultaneously. Let's run the program. So we are starting to see the argument that we have passed. Let me pause the video and get back once we get the full result. So ultimately, if you look at the results, they are actually indeed running simultaneously. Basically, whatever the object that you send in here is sort of acting like an identifier for this section of synchronized code. But if you observe, still we are dealing with only one lock. For this object, there was only one lock and is grabbed by some thread. And in here, the thread needs to grab the lock of whatever the object that we give here. And that's why these two sections can be executed simultaneously, because there are two different locks from two different objects. But let's say somewhere else in the code you have another section and you have this as a keyword which you have already used elsewhere in another synchronized block. Then in this case, no two threads can enter inside and execute this section and this section simultaneously, because only one thread can acquire lock of this object. So when any of the thread is executing either of these sections with the same object, then no other thread can enter inside the synchronized block which is having this as an argument. Hope that's pretty clear. Let's undo those changes and save the file. Let's continue in our next video. In case if you wanted to access the static method, like in this case we have write to file as static method, then you might want to acquire lock on the class, not the instance. So how do we acquire lock in a synchronized block? Instead of passing in the object, we'll pass in the class name. Let's copy it and paste it over here, dot class. Now you can access the static methods using the class name like so. Hope that makes sense. See you in my next video. In this video, we're going to talk about some of the terminologies used in multithreading. All the terminologies that I'm going to talk about can be seen in this real-world example. Let's talk about mutual exclusion. Just as we allowed each one of these customers to have exclusive access to the changing room, we allowed exclusive access to synchronized block for our threads. This phenomenon is called mutual exclusion. It's as simple as that. Now let's talk about something called an entry set. In this example, people kind of entered into this region. Now these set of people are called entry set. Similarly, all the threads which are trying to access the synchronized method are said to be in entry set. Now let's talk about something called wait set. We need to talk about inter-thread communication and the methods like wait, notify, and notify all to be able to understand what is wait set. But just for the completeness of this video, I'll try to explain it. Although it's hard to correlate wait set in this real-world example, I'll try my best. Let's say one person entered this room by acquiring the lock, of course, and assume that for some reason in the middle of his activity in the changing room, he decided to sacrifice and let some other person to get exclusive access to the changing room. So he will inform the monitor, who is sitting and managing everything in here. Now the monitor will grab the lock from him and he will send that guy to another room called wait set. Now the guy who sacrificed the room for others, come and stand in here. Now the lock is made available for other people in the entry set. All the people who are residing in the wait set will come and continue with their activity in the changing room at later point of time only after somebody notifies them that they can continue with their activity. But of course, again, only after acquiring the key and one at a time. You will better understand what I'm saying when we talk about inter-thread communication. We're going to talk about it pretty soon. In programming terms, when a thread calls wait method of a particular object, the thread will temporarily release the lock of that object and makes it available for other threads. For now, I think this example should suffice. You will understand more on wait set when we talk about inter-thread communication. Now let's talk about monitor. In our example, we have already talked about a guy who is sitting near the changing room and handling the keys to one customer at a time. We also named him as monitor, as he is monitoring all the activities going on in here. He manages the changing room, entry set, and wait set. It's as simple as that. So far in our examples, I was mentioning that each object or a class is associated with a lock. I have said so for simplicity's sake, but the right way to say it is each of the object or the class has a monitor associated with it, and the monitor takes care of giving exclusive access to threads on the synchronized section of that object or class. So when I said a thread acquired the lock, I actually meant a thread acquired the monitor. And when I said the thread entered the synchronized section, I meant the thread owned the monitor. And when I said released the lock, I meant releasing the monitor of that object or class. However, if you find it convenient to use the term lock, you're most welcome. That's what typically used for simplicity. Hope that makes sense. See you in my next video. Okay, in this video we're going to talk about volatile keyboard. Assume that we have a code, and in that we have a variable with the value of 10 assigned, and let's assume we have a couple of threads T1 and T2, and in T1 all we are doing is we're incrementing the value of C for say 7 times, and in T2 all we are doing is we are periodically reading the value of C from the memory. So in our memory the initial value of C would be 10. Let's assume that we have a dual core processor and each one of these threads are running simultaneously on each one of these cores. So T1 goes in core 1 and it tries to perform the operation of incrementing the value 7 times. Now for the sake of performance, the way the code is executed is the operating system is going to copy all the required variables into a local cache that resides in the CPU core, and the processor is going to use that cache to perform operations. So it's going to copy the value of 10 initially to the cache, and it's going to increment the value by 1, which will make it to 11, and again it increments the value which will make it to 12. Whatever it is, it's updating the value in the local cache, not in the actual memory, because it's expensive to read the value from memory and put it back in memory, again read it every time you want to increment the value. It's going to cost the performance. So operating system uses the local cache for that. But we have a problem associated with it. Thread 2, on the other hand, is not getting the updated value. When it is trying to read the value of C, it's still getting the value as 10, while in the local cache of core 1, it's already incremented a couple of times and the value is 12. So in this kind of mechanism, there is no guarantee when the OS will flush all the data in the cache back to the memory and then make the data available for thread 2. So the point I want to make here is thread 2 is not getting the updated value. So the solution is, if you make this variable volatile, what's going to happen is all the read-write operations will be performed directly on the memory. This variable will not be copied into the local cache. For every increment, the value of that variable would be fetched from the memory and is written back to the memory. And so we always are guaranteed to get the updated value. So in multi-threaded programming, this is very important at times. In our next video, we're going to talk about inter-thread communication, and as part of the example, we're going to have to use the volatile keyword. So we'll see an example of it in next video. Now let's also talk about the happens before relationship. Let's say there are two threads, thread A and thread B, and let's say thread B is dependent on the write operation of thread A. In that case, we want to make sure that the write operation happens before the read operation. So in other words, it's basically just simply the results of a write by one thread are guaranteed to be visible to a read by another thread, only if the write operation happens before the read operation. Hope that's clear. Alright, see you in my next video. In this video, we're going to talk about inter-thread communication. Don't let that term scare you, because it's just about three methods which are in the object class. Those are wait, notify, and notify all. And as we would normally do, let's take a look at the real world example before we jump into the code. So we have an entry set, the changing room, and the wait set, and everything is being monitored by the monitor, obviously. One person enters inside the changing room by acquiring the lock, and let's say the person who just entered has decided to sacrifice the room for some other person in the entry set. So he's going to handle that lock back to the monitor, and he's going to be going to the wait set. And the next person who jumps in, of course by acquiring the lock, is going to finish the activity. But before finishing, it's the responsibility of this person who's using the changing room to notify the person in the wait set that he's done using. Once he does so, this guy is again going to handle the lock back to the monitor, and monitor will call the person in the wait set again to continue with his activity in the changing room by handling the lock to him, of course. So we've talked about two major things here. One is this person, when he was here in the changing room, he said, I want to wait in the waiting set. And the next person who has just entered is going to notify this person once he is done with the activity. Now keep this entire scenario in mind. Now let's move on with our code example. So for the sake of this example, I have created a couple of files. In this file, I just have one method that will take in one integer variable, and all it's going to do is it's going to find sum of all the digits. I mean, if I send the value as 3, it's going to find the sum of 3, 2, 1. If I send the value 5, it's going to find the sum of 5, 4, 3, 2, 1, like so, and it's going to return the result. I've created an object of that class. We have a couple of threads, T1 and T2. From T1, I'm trying to get the total, and this variable is actually a static member of the class wait notify example. And from thread 2, we're using the same object that we've created here to find the sum of, in this case, the number 10, and we're assigning that value to this variable. Now what we want to make sure is we want to make sure that T1 starts first and T2 start second, and for that I've just have a sleep method called. So in a way it's almost guaranteed that T1 is going to be called first, then T2. In here my task is to display the total, but since T1 is starting first, the total would display as 0. Let's run the program. There it is. But what I'm expecting here is 55, because that's what the result that we would get from that method. So what is the solution for this? So what I'm going to do is I'm going to have another variable which is going to be static boolean done as false. Once we found out the total and updated the value, we're going to say done equals true, and in here we're going to have a while loop which will check to see if the done is true or not. If it is not true, then we want to continuously loop forever until the done becomes true. Now if I run the program, we will have one problem with this. Let's go to the console. The program is running forever. So what's actually happening? In thread 2, we have set the value of done to true, but seems like the value is not updated in the actual memory. It is updated in the local cache of the processor core where thread T2 is running. So guess what? Let's stop this program. What is the solution? Make this variable volatile. Let's run the program now, and we would see the result we're expecting. Pretty well and good. No, actually pretty bad, because this is definitely a bad practice. This is like we're constantly polling the status of done, and we keep on looping through for a very long period of time until this is set to true by some other processor. This is definitely a performance overhead for larger applications. So guess what? Let's make use of the inter-thread communication. Let me get rid of all the code in here. We no longer want to use this. Let's save the file. And what I'm going to do now is, since we want to let T1 wait until T2 finishes and gets the result, what we want to do here is I'm going to call the wait method inside this object from inside here, dot wait. So basically what this wait method does is it's going to release the lock of this object and is going to wait until some other thread calls the notify method of the same object. But clearly we have a problem here. Since wait method releases the lock, we have to be in the synchronized block or in synchronized method. Even in our changing room example that we've just looked at, there is no purpose of lock without the changing room. And even in here, there is no purpose of wait unless we're inside the synchronized block. In here, we cannot make the run method synchronized. That's because we're never going to call the run method directly. We're going to call the start method, and internally Java implementation is going to call the run method. So we cannot make the run method as synchronized. So the only option we have is to use the synchronized block. And in here I'm going to pass in this object, and within the synchronized block I want to call this method wait. This is going to throw interrupted exception. We'll talk about interrupted exception in a while. Let's delete comments. Now the thread will go into wait set right here by releasing the lock. So some other thread can grab that lock. The only thread we have in here is thread 2, on which thread T1 is dependent on. So in here, after we do the operation, we're going to notify the thread that is waiting in the wait set by using the notify method of that object. And again, this method needs to reside inside the synchronized block. I'll type sync, control space, and press return. I'm going to have these two statements inside this, and I'll pass this object as an argument. Now, by calling the notify, it just means that thread 2 is willing to give the lock. Do take a note, is just willing to give the lock, but not handling the lock directly. If you have any more instructions after the notify method, the lock will not be released by the monitor until all these instructions are executed. So with notify, thread 2 is just informing the thread in the wait set that it can continue what it is doing. It's as simple as that. Now, guess what? We're pretty much done. Let's run the program. Pretty well and good. Also, do take a note that this object really has no purpose. In fact, the argument that we're sending to this synchronized can be any object, literally. Ultimately, what we want to accomplish is we want a unique identifier for these two synchronized sections. Hope that's clear. Let me prove that to you. Let's take any random class. Maybe I'll take sync example, new sync example, and let's say I want to use this object and I want to wait on that object. Same thing goes here. So in here, since T1 enters first, T1 is going to acquire the lock, and when it comes across with the statement wait, it's going to release the lock for other threads in the entry set, and it's going to put itself in the wait set. Meanwhile, thread 2 enters by acquiring the lock, and it does whatever it needs to do, and it will call the notify. The notify is just a signal that all the threads which are in the wait set can now join back in the changing room and continue what they're doing, but only after monitor handles them the lock. And monitor handles them the lock only after making sure all the rest of the instructions in this thread are executed. Now let's run the program. Very well and good. Let's undo those changes. Alright, now let's talk about interrupt. Let's say I want to somehow make this thread wait forever. So I'll run thread 2 first and then thread 1. Definitely this will keep this thread in wait set forever because nobody else is really notifying, because that instruction is already executed. But this is not guaranteed way of keeping this thread in wait state. Let's run the program and see what happens. Guess what? It's waiting forever. Let's stop the program. Sometimes you might want to interrupt the thread which is waiting for a very long time. So what are you going to do is, from the calling thread, I want to interrupt the thread T1 after waiting for, say, thread.sleep 10 seconds. Before 10 seconds, if this finishes executing by itself, that's great. But if it doesn't, then I want to force interrupt the waiting thread. Let's run the program. So it's going forever. The main thread is going to wait for 10 seconds at max and is going to interrupt. When the interrupt happens, it's going to throw the interrupted exception. The wait method is going to throw the interrupted exception, and that's why we have try catch block. It's a checked exception, by the way, as you can guess. And when the thread is interrupted, the flag of is interrupted is going to be set to true, and in here if the thread T1 is interrupted, you might want to do some operation. You might want to execute a set of instructions that are meaningful. So we don't want to get there at the moment. Okay, let me just undo everything just to demonstrate to you what is thread interrupting. Alright, let's talk about one last method we have, which is notify all. Notify all is very similar to notify, except it's going to notify all the threads that are waiting in the wait set. So let's assume we have another thread. Let's call it T3, and even that is waiting for the thread T2 to execute, and I want to start the thread. I want to start thread T1 and T3 before T2 starts. Now let's run the program. Pretty well and good, except okay, here is the problem. We just said notify. So the notify method is going to notify only one thread in the wait set. So either of these two threads may get the notification. The other thread will keep waiting forever. So we need to use, as you can guess, notify all. Now the program will run smoothly. Pretty well and good. See you in my next video. In this video, we're going to talk about thread group. Thread group allows you to group a bunch of related threads together so that you can perform operations like interrupt, suspend, destroy, etc. with just a single method call of this thread group object. And here I've created an object of thread group, and I have given it a name by passing string as an argument to this constructor. And as a first argument to the thread constructor, I'm going to pass this group object that will make this thread T1 to be part of this group. Similarly, I have 3 threads added to that group. In T1, I'm going to wait for 6 seconds before I print this message. In T2, I did the same with 9 seconds, and T3, 20 seconds. I started all the threads, and in main thread I'm just trying to sleep for 10 seconds. And by this time, after main thread waits for 10 seconds, I'm assuming that thread T1 and T2 should be finished, but thread T3 must still be sleeping. So this statement, which will get the active count, is going to return me the value 1, because only one thread is active at that time. And using the thread group object, I'm going to call the method list. This is just going to show the details of all the threads in the group. Let's run the program. After 6 seconds, thread T1 finished, and after 9 seconds, thread T2 finished. We got one active thread at this point of time, and we've also listed out all the details. And finally, we have our thread T3 finished executing after sleeping for 20 seconds. Likewise, we have got many such methods inside thread group. You can always explore them when you get chance. So we can destroy, interrupt. We can also make use of wait, notify, and notify all, suspend and resume. You can stop the thread. You can go through the description on the right, and I believe all these methods are pretty much self-explanatory by now. And that's it. You can explore more on your own. In this video, we're going to talk about deadlock. Deadlock is a situation where 2 or more threads will wait forever to acquire the lock owned by some other thread. In this example, I have created a couple of objects of the class object. We also have a couple of threads, and in each one of these threads I have nested synchronized block, which means a synchronized block inside another synchronized block. In thread T1, before I enter inside this section, the T1 needs to acquire the lock of object 1, and inside this I'm waiting for a second, and to enter inside this sub-synchronized section, the thread needs to acquire the lock of object 2. In thread 2, it's the other way. First we need to acquire the lock of object 2 and then object 1. This is a good example for deadlock. Now what's going to happen is, let's say T1 started first, so it enters inside this block by acquiring the lock of object 1, and it waits for a second, or rather sleeps for a second. While the thread T1 is sleeping, thread T2 acquires the lock of object 2 and it sleeps for a second. And when thread T1 enters this section, it needs to acquire the lock of object 2, but it cannot because object 2 lock is acquired by T2. Same in here. When T2 enters this section of code, it needs to acquire the lock of object 1, but it's not possible because it's already acquired by T1. So both these threads will wait forever to acquire the lock, and that will never happen. If I run this program, these statements inside this nested synchronized block will never get executed. Instead, both the threads will be in waiting state. Both the threads will keep waiting for each other forever. So let's terminate this. So as a solution, the solution is, let's have the ordered way of requesting for locks in all the threads. Instead of saying object 1 and then object 2 in thread 1 and object 2 and object 1 in thread 2, let's make them identical. So in here I'll have object 1, object 2, just as we have in T1. Now this will definitely solve the problem. Let's assume that T1 started first. It acquires the lock of object 1 and is going to wait or sleep for a second. Meanwhile, when T2 starts, it cannot acquire the lock of object 1, and so it's going to wait for the lock to be available. And T1 acquires the lock of object 2, executes this statement, and releases the lock for both these objects and is made available for T2. And T2 then continues and executes the code inside it. Let's run the program. Pretty well and good. Alright, see you in my next video. Alright, multithreading is a pretty vast topic and there are even books written for it. But I think we are starting to feel tired of multithreading by now. And the truth is, we have just covered 60% of what I've planned to cover. So just for recreation, I'm going to give you a brief pause in the multithreading chapter, and we'll continue with that at a later point of time. Meanwhile, we'll get into more interesting Java topics. See you in my next video.
I hope you enjoyed this tutorial. Please like and subscribe. The link to the next part of this course is in the description below. Also, if you want to learn Java with practice, with quizzes, assignments, coding puzzles and interview questions, I cannot do that on YouTube. So you need to take this course on my own website. The link is in the description below. I'll see you in the next part of this course.